Welcome to part 3 of the Siglent SDG7102A review. Siglent has taken note of the issues I've shown in this review of this beta unit and is working on them now. They've promised to send me an updated unit to review when it's ready. Let's look at the frequency sweep mode. It does linear log sweeps between two frequencies. This is useful for tuning, filter adjustment. There's lots of things you can use swept frequencies for. It allows for extra signal time pre and post sweep. The pre-sweep is currently not working, but it should be working after a firmware update. The rear panel sync signal can be enabled. It goes high at the start of the sweep and low at the center of the sweep, and it can only be used with one channel at a time. You can have the channels doing different types of sweeps, but you can only use the sync signal with one of them. There are two rear panel marker outputs. One is assigned to each channel. It would be nice if both could be used on the same channel. That's a firmware update suggestion for me. The marker is a 100 nanosecond pulse, and it's too narrow to see on the scope during most sweeps. I'd like to see it go high at the marker frequency and low at the end of the sweep. That's another firmware update suggestion. So now I have the function generator in sweep marker mode. Notice I have it set up for a 10 millisecond sweep time and a 10 millisecond back time, which is dead. So you can see the sweep here, then the dead time. The blue trace is the sync signal coming out of the back, which I have turned on. Let's come back here. And so trigger out. If I turn this off, it goes away. So there it is. And then I have a frequency marker set up, which I'm triggering on. Now the actual frequency setting for the sweep, I have it sweeping from 430 kilohertz to 480 kilohertz. Now the marker I have set for 455 kilohertz, which is right in the middle of the sweep. So you can see that the sync goes high at the beginning of the sweep and low at approximately the middle of the sweep. Now if I change this marker frequency, let's say to 435 kilohertz, you'll see that the marker now shifts over toward the beginning of the sweep. We can go to 430 kilohertz. And so now it is at the beginning of the sweep. So let's look and see how well what that looks like in actual timing. Okay, so now we're looking at the beginning of the sweep. And you can see that the marker comes up just past where the 430 kilohertz starts, but the sweep is delayed by about 2 microseconds from the beginning of the sync. Now the marker is not very wide, so it's good to sync on, but I don't know that you'd be able to display some sort of any kind of blip on let's say you wanted to modulate Z with it on your scope. I don't know that you'd see that. So you can see here we're at 500 nanoseconds per division. So that marker is really only a couple hundred nanoseconds wide. It's pretty narrow. So now let's go back to the full sweep. There we are. Oh, I'm a little bit too much here. There, that's better. So now let's go back on the signal generator. And let's look at the time settings. So if I change the sweep time to 15 milliseconds. You'll see, yes, it sweeps out and the dead time is 10 milliseconds. So let's keep that there. Now let's add a hold time at the end of 5 milliseconds. Okay, so I've got 15 milliseconds for the sweep time, 5 milliseconds hold at the end, and so that gives me 20 milliseconds. Let's try and add some hold time at the beginning, 5 milliseconds, so that should get me up to 25. That doesn't work, and that's too bad, because that's normally where you'd want the hold time in the sweep. You'd want it to turn on and stabilize before you actually go through your frequency sweep. So there's a bug in the firmware for the sweep mode. So let's see what's inside this unit. This thing, I'm told, shares the case with the Siglent RF generators. So these ones on the front bumpers do not come off. I found it's better to loosen them just a touch, but just leave them in place. Let me back off a little bit more so you can see what I'm doing. These rear bumpers come off. I actually like these bumpers on the front and the back. They protect the unit if you happen to set it on the floor or push it up against something. I think they're actually a good idea. I know some people complain about them. Oh, let me get those screws out of there. Oh, I'm stuck in the screwdriver. There we go. And these here are a different size. Let's try this one here. There we go. There. Okay, so let's lay this down here, perhaps, and let's zoom in on this a bit. Okay, so this is the front panel here. It's shielded. There's a ribbon cable that comes up off of here. I assume that's the digital lines, and then there's some wires here that come off the board. I'm guessing that's the power supply. I don't know if you can see it in there. The 4 BNC connectors are on the front panel, and it looks like the cables are crimped on and then heat shrink. There's a bunch of interconnect cables here, all with SMB connectors. I don't know what these parts are. I'm guessing they're regulators. Power, maybe perhaps power op amps. Let me back off a little bit here. Okay. This daughter board here is kind of interesting. It's using a DDR memory connector and sitting there. That's nice reuse of the of a inexpensive connector. So a lot of the key components for this thing, probably all the high-speed analog stuff, is under this heatsink here and all bolted together with these cables I'm not going in there. I just had permission to take the lid off, not completely disassemble it. So we're looking down into the SDG7102A, and it's got some interesting construction. You can see over here, this is the switching power supply. The power jack comes in and comes over here. This cable clamp seems to have come off. I think the wire was too short for it, so it's just flapping around in the breeze. But mostly it looks very nice. There's a lot of SMB connectors you can see here. This seems to be the main board, output board here. And there's a lot of chips under the heatsink here. I assume these are regulators, and there's some more stuff underneath. I expect there's some sort of FPGA or processor here. It's got 3 fans on the side, and I kind of like this design. Instead of having one big noisy fan, it has 3 smaller, quiet fans, and you can hear them, but just barely. When I have anything else in my lab turned on with fans, the other instruments completely dominate. So this board is actually plugged into a DDR memory connector. So this is kind of an interesting way. So they've designed this board with a footprint that's compatible with DDR memory, so they can reuse a common connector. It's a good choice. Lots of nice beefy heat sinks with good airflow. The fins are all going through. I'll show you some thermal images in a minute. The hottest spot in the unit I can see is actually in the power supply here. This piece up here is the crystal clock in an oven. So this is the ovenized clock, and it actually is riveted onto the back of the unit with the plate over it. This is the only feature that you have to buy with the unit. All the other upgrades apparently can be bought afterwards. Performance upgrades, capabilities are all just software keys. However, the crystal oven is hardware, and that has to be ordered with the unit. We're looking at the left side of the unit with the cover off. You can see the back panel's to the left, the front panel is to the right. The power supply's down there in the front. You can see the big analog daughter board with the big heatsink on it. There's SMB cables that go from the analog daughter board down to the motherboard. There's SMB cables on the right side of the daughter card that go to the BNCs on the front panel. I think that's a power connector. That ribbon cable, I believe, is some sort of digital I/O down to the motherboard. And then there's a bunch of twisted pair cables that may be high-speed digital. I'm guessing are high-speed digital lines up to that daughter card. For here, we have the big fin thing, which I think is the CPU, and then there's an air duct to the CPU heatsink. Down on the left, we have the power and fuse connector, the RJ45 internet connector, the 2 USB connectors, the digital I/O for the 16-bit digital output, the 4 BNCs on the back panel, and the crystal oven attached to the back panel. On the right, we have a ribbon cable that goes up to the front panel. And then there's what I believe is an FPGA daughter board with a heatsink that's mounted in the DDR socket. Let's look more closely at this FPGA daughter board. We can see down at the bottom there's a JTAG connector, and we can see the fiducial marks for assembly. Now we're looking from the back side of the unit toward the front. You can see the SMB cables on the left side to the from the daughter board to the front panel, the ribbon cable to the front panel, and over on the right, the power connector to the front panel. Now, if we look in these highlighted areas here, I believe that's all power conversion along the edge of the board. These two bricks are actually brick-looking things are actually hybrid power converters, and they're monolithic power systems, complete units with oscillators, voltage reference, coils, everything inside, and QFN packages. The temperatures I'm going to show I did with my Unity UTI 260B thermal camera. My version of this camera always displays temperatures that are higher than actual. That means the actual temperatures are lower than this camera indicates. And yes, I do have the thermal emissivity turned all the way up to 1. The temperatures in the SDG7102A will be higher with the cover removed because the airflow is not as designed. And even with the cover removed, all of the temperatures are fine. We're looking from the front left down at the unit with my Unity 260 thermal camera. The thermal camera takes simultaneous thermal and visual images, and the temperature readings on it tend to be 1 to a few degrees high. And the emissivity is turned all the way up. This camera just reads high. Anyway, you can see here on the left side, here and here, that the hot spot is the power supply. Now, if we look here, you see this the finned heatsink here. This is on the daughter board that's on the DDR board, and the heatsink itself is cool, but there's heat coming from around it, and some from this chip here, and these two chips here appear to be warm. This stuff up here at the top is just reflections from up here. That's not real. Now we're looking from the front right corner across the unit. So again, the power supply here is the hot spot, and you can see then the heat coming from the daughter board here, and you can see that there's a couple of warm spots coming through the holes in the heatsink above the analog daughter board. Now we're looking again from the right side of the unit down at the heatsink over the big analog daughter board. And again, you see some heat coming through the holes, but the heatsink itself looks clear. The hottest spot up in the top left is, again, the power supply. And so let's go to the next slide. Here we're looking from the right side of the unit at the power supply. Again, it is the hottest spot. It says 58.5. It's probably a bit cooler than that, but none of the temperatures in this thing are out of hand. They're all reasonable, all 50, 60 degrees, or below. They're all below 60 degrees C, and most of them are well below 50. So I'd have no problems leaving this thing on all the time. So here we're looking down from the left side of the unit along the back. This heatsink here, the big one with the fins, I believe is over the CPU. And then this duct comes from the rear fan on the right side and ducts the air through the fins on the CPU. So there's something hot on the board behind the CPU. You can see it through the fins here. And then this hot spot here, which is the hottest spot on this image, I believe is this chip right here. Now we're looking from the left side of the unit near the front across the unit. Again, so the power supply is in front. You see the daughter board is warm. There's some warmth below the CPU heatsink. You can see through the ductwork here that there's some hot spots in there. And there's some hot spots on this board and some under the board too. So this is a daughter board that's sitting above the main board, and there's some heat coming from below that too. But again, nothing out of hand. So now this is from the front side of the unit on the left side, looking across the unit. So here's the daughter board. You can see the hot spots below and the heat sink. Same thing. So here's some more views under the large analog daughter board, and it's warmer under there, but again, not bad. So now we're looking from the right side of the unit near the front, across it, kind of, and the power supply is the hot spot above, and you can see these parts here warm around this daughter board again. Some warmth on these chips here. Something coming from there, but nothing out of hand. This is kind of interesting. This is looking at the front screen of the unit. You can see here near the bottom of the screen, it's warm, and it's just slightly left to center in the screen. And I wonder if that has anything to do with the fact that this bottom left corner was coming loose at times. Now we're looking at the crystal controlled oven crystal oscillator, and that's right here. And you can see it's a little warm. These things that appear to be hot spots along the back aren't really there. They're reflections off this shiny panel. So the main thing we're seeing here is the oven and a little bit of warmth below it. Now we're looking on the right side of the unit along the back. The crystal oven is right here. You can see in the thermal image, we can just see the top corner of it. What we really see is here, this spot is hot. I believe that's this chip here. And again, the power supply is the hottest spot. Now we're looking from the back and along from the right side of the unit, sideways across the unit. This is the large heatsink over the big analog daughter board. Again, you see the hot spots through the holes. The heat from coming from below the heatsink on this daughter board. And some other chips. This one appears to be hot. This appears to be hot. This appears to be hot. Okay, now they're hot, but again, they're in the 40 to 50 degree C range. That's fine. So here, again, we're looking, this is from the right side of the unit, but from the rear and a little closer, and we're kind of moved in closer to this daughter board here. And so we can see here that a couple of these things are hot. These are probably voltage regulators, would be my guess. There's something hot right here. Again, heat coming from here. So we're looking at the 0 dBm output of the SDG7102A at 100 megahertz. At this frequency and every other frequency I looked at, there was essentially no measurable harmonic distortion down to minus 80 dBc, which is as low as I looked. That's excellent and much better than the minus 55 dBc spec that's published. Now, I only looked at 0 dBm. It's possible that the distortion would go up at lower levels as you're using less bits to create the sine wave, but I did not try that. So here we've got a 5 kilohertz span with a 500 hertz per division, and the resolution bandwidth of the spectrum analyzer is set to 1 hertz. We can see now that I have spurious peaks around the carrier, but they're all down more than minus 80 dBc. That's much better than the minus 65 dBc spec. That's excellent. Now I've changed the span to 500 hertz, so each division is 50 hertz. I'm still at the 1 hertz resolution bandwidth for the spectrum analyzer. You can see here the spurious peaks are down minus 80 dBc. It's still excellent. And it looks like the phase noise is at 100 hertz offset is less than minus 77 dBc. And I have the spectrum analyzer locked to the function generator. Now, to tell you the truth, at this level, I'm not sure that what we're seeing here isn't coming from the spectrum analyzer and not the signal generator. But it's good, so I'm not going to say too much about it, but this is what we're seeing here. It could be either. What were the issues with this beta unit? It had a bad rotary encoder. That's not acceptable on any instrument, especially one in this price class. The output level errors and self-calibration didn't fix it. Again, those are issues that have to be fixed. Firmware fixes that need to be done. The 128 QAM mode didn't work in IQ mode, and the pre-sweep and the frequency sweep mode needs a tweak. Anyway, Siglent will correct these issues. They're very good about fixing issues that are identified. And that's one of the reasons I own several of their instruments. What is special about this instrument? It has very fast rise and fall times. In fact, it's faster than most pulse generators. And it works out to be excellent for semiconductor rise, fall, and storage time testing, and I'll have a separate video on this subject. It has a very wide output voltage range, plus or minus 12 volts offset with a 12 volt peak to peak swing for up to plus or minus 24 volts into a high Z load, and up to plus or minus 12 volts into a 50 ohm load. But because of this big swing, you have to be very careful with the 50 ohm instrument inputs. It can dump 2.9 watts or the equivalent of 34.6 dBm at DC into a 50 ohm load. And if you have a 50 ohm input scope, that might just smoke the input to your expensive oscilloscope. So you got to be very careful. It will do these large swings at 20 megahertz or less, or 40 megahertz for a sine wave. And the measured rise and fall times for this large swing is 2 nanoseconds or less. That's excellent. It has a differential outputs on both channels that are independent. It only has a plus or minus 1 volt range into 50 ohms on each side, so 100 ohms differential, but it has 500 picosecond rise and fall times. That's excellent. It has a very accurate frequency clock, basically the oven-controlled crystal oscillator option, and it's spec'd to be better than 150 parts per billion after a year. So 100 initially plus 50 after a year, and it's expected to drift less than 1 part per billion, not parts per billion, per degree C. It's got a very clean RF output up to 1 gigahertz with all the standard modulations, so it could easily replace an RF generator in your lab. It's a $3,000 option, but it does IQ modulation from 250 symbols a second up to 500 million symbols per second. That's very fast. It's calibrated up to 150 megahertz bandwidth, but with certain settings, you can get up to a 650 megahertz bandwidth with your IQ modulation. It has a very wide frequency range for a function generator, up to 1 gigahertz in sine wave, 240 megahertz in square wave, and 312.5 megahertz in pulse, and triangle waves up to 10 megahertz, which doesn't seem that fast compared to other things, but is very fast for a triangle wave out of a function generator. It does the pseudo-random bit sequences up to 312.5 megabits per second. And that's not as fast as some things require and much faster than others, but it's a very useful feature. It does arbitrary functions up to 2.5 gigasamples per second. That's very fast. And it does pseudo-random noise. I measured 370 megahertz bandwidth, and I did not notice that the bandwidth was adjustable, but apparently it is. I overlooked that when I was evaluating the unit. It has a rear 16-bit digital output, which outputs up to 1 gigabit per second. And it puts out a differential digital signal, and they have a converter which slows that down the output with TTL levels. That's a unique output in a function generator. What things would I like to see in this unit? I'd like to see in the frequency sweep mode, I'd like to have the option for the markers to be a level change instead of a pulse, similar to the way the sync output works and easily visible on the oscilloscope sweep. The option to use both markers on one channel to mark, so I could mark 2 points on the frequency sweep. I'd like to have the digital output of to drive relays. So right now it comes with a SMAs out for the high-speed differential output or a TTL converter. I'd really just like a simple cable to a 50-pin D connector so I could make a circuit to drive relays. Because often in test sets, I'll put an instrument in and I'll use one instrument over another because I can use that instrument to drive relays in my test set. And you just need a simple cable for that, and that would be an easy feature for them to add. And I'd like to see an improved keyboard interface. Right now, you can do everything with an external keyboard and mouse. The mouse interface is excellent. The keyboard interface is very clunky. I'd like the ability to type like engineering exponents, PNUM, on the keyboard and not have to click on the screen with the mouse or hit the front panel to get the exponents. So this instrument is a very unique instrument that can be used in place of many instruments other than an arbitrary function generator, a fast edge pulse generator, RF generator with modulation, and a digital pattern generator. It has many more capabilities than I had time to explore in my brief time with it. Siglent has promised to lend me another unit once they've addressed the issues I identified in this review. If you have things you'd like to see when I get another unit, please leave them in the comments. If you liked this video, please give it a thumbs up. If you haven't yet, please subscribe to this channel and click the notification bell to get notices when I post new videos. Thank you for watching.